Hello, my name is Matthew Farrell. I'm a postdoc with Cengiz Pehlivan at the School of Engineering and Applied Sciences at Harvard University. Let me share my screen so we can get started. Okay, so this work is called Capacity of Group Invariant Linear Readouts from Equivariant Representations. How many objects can be linearly classified under all possible views? Okay, so this work considers equivariant representations and their coding properties. So what do I mean when I say equivariant? Let's say we have some input stimuli, like this picture of a dog. We feed this into a brain or an artificial neural network if you want. And then we look inside at the neural representation. And we assume that each input stimulus gives rise to a point here in neural space. So this could be like the firing rates of the neurons, right? So we get a single point here. And now we consider the case where the input shifts, right? So here it's shifting by 90 degrees, right? And here I have joined the left and the right side. So there's a periodic boundary here for mathematical convenience, but you can basically think of this as a translation of the image. And equivariance says that the neural representation should transform in an analogous fashion. So here it would go around in a periodic way. Okay, and so if you have different input stimuli, like here's a picture of a cat, then the same thing will happen. As the cat picture of the cat translates, then you'll trace out this manifold here. Right? Okay, so this type of representation can be formalized with group representation theory. And once we have this kind of representation, we can ask questions like, how easy is it to read out object identity? For instance, dog versus cat. And how many neurons are needed to be able to store X different objects so that they can still be easily distinguished from each other? Okay, and these questions are essentially questions of the code's capacity or expressivity. Okay, so to measure this, we use this notion of perceptron capacity, right? So this is given by the fraction of possible labelings here. So where the label can be +1 or -1 of the object manifolds such that there exists a separating hyperplane, right? So if there's a separating hyperplane, it means that the perceptron can solve the classification problem. Okay, so over here you see, so this manifold has a label +1, this manifold has a label -1, and we have a separating hyperplane. Okay, so if we just get rid of these manifolds for a second and consider the problem where we just have points, right? So for points in general position, the perceptron capacity is known and is given by this quantity here, right? So, and here n is the number of neurons, and P is the number of points, right? Okay, so we have an answer in this case, and we want to extend this to the manifolds, right? So here are the manifolds again. All right, so to work with these manifolds, we use this group representation theory, right? So we assume that we have an input X that transforms like Gx, where G is an element of a group. Okay, and a group is this mathematical object that has nice properties, right? So elements in the group have inverses, for instance, right? So it just kind of behaves nicely. And Gx would be like a group action. So G, little g, could represent like a translation or something applied to the image X, right? And the equivariance condition says that the neural response, here I write this as R of X, satisfies this condition here. So basically, as I transform the inputs, the representation transforms according to this pi of G. And pi is a linear representation of G. Okay, so the pi of G are matrices, and they form a group as well with the same structure or analogous structure as G. And what I mean by that is that pi of G, G prime equals pi of G prime. Okay, so that's what that condition means. So essentially the matrix group formed by the pi of G respects the structure of the group here, big G. Okay, so now that we have defined what our representation looks like, so we assume that these manifolds are given by these pi of G R of X, then we can go ahead and do the theory, compute the perceptron capacity here, this F, right? And so our main result is that the perceptron capacity for these manifolds is given by F of P comma N naught, right? So previously N was the number of neurons, but here N naught is the rank of this matrix pi of G averaged over G. Okay, and this allows us to predict the capacity of many models that have an equivariance condition like HMAX and convolutional neural networks. Okay, so let's see what that looks like. So for HMAX, right? So this is a model of the visual system, the early stages of the visual system that puts together simple cells and complex cells. So the theory says that the relevant dimension here, N naught, is the number of distinct orientations of the simple or the complex cells, right? And so here we actually, apply this model to the image and actually compute the number of separable dichotomies and see that it experimentally matches theory. And then, so now we do the same thing with convolutional neural networks. And here the relevant N naught is the number of filters used in the convolutional layer. Right, so here the blue line is just after one convolutional layer. The orange line is after then applying a max pool to the output of that layer. So it's a 2x2 max pool, which our theory also predicts will, in general, decrease the capacity. And then the green line is for following up with another convolutional layer. Okay, and finally, I'd like to thank my collaborators, especially Blake, who worked with me closely on the material. Thank my funding source and point to the archive paper that has the same title for more details.